Show up.
Discrepancy, whatever.
So Dr. Zabel had a work-related commitment this morning, so he asked me to go ahead and take the class for him today, so that's why I'm here. And what he asked me to do was go through gas laws and go through some of the material and do some problems with you on gas laws. So that's what we're going to do. And so what I'll do is we'll just talk about some of the ideas we actually talked about a little bit in lab, just to kind of refresh your memory on what moles are in ideal gas laws, and then I'll spend most of my time developing some of the kinetic theory of gases, which is what we'll look at how gases behave at the atomic level. And then we'll end up talking about 4 different kinds of basic thermal processes as they relate to gases involved in those thermal processes. So how gases behave in an isothermal, isobaric, isochoric, and adiabatic processes. And we'll do a few problems. Mostly these are problems on the worksheet that is on the website. I think I threw maybe one that isn't in there. And if there's time, I'll do a couple more from the book. One of your homework problems and another one. I just don't know if there'll be time. So we'll see how it goes. So let's just go ahead and dive in. The first thing just to remind you of is this. When we talk about gases, kind of like when we talked about liquids, fluids, one of the things, whether it's liquid or a gas, one of the things we need to do is use the concept of density rather than the concept of mass to describe them. But when we're going to talk about gases, and especially their behavior at the atomic level, we need another way to talk about the amount of a gas other than its mass. In fact, we particularly want to know the number of atoms or molecules in the gas, but that's a huge number. And so if we did all our calculations with the number of molecules, we'd always be dealing with huge, huge numbers. So in order just to talk about the number of things that are in a container of gas, number of molecules in a container of gas, and keep that number relatively small, this concept of a mole was introduced. And a mole is the number of atoms that are in 12 grams of a sample of carbon-12, the isotope of carbon that has 6 protons and 6 neutrons, so 12 nucleons. And then by experiment, what was found out was that that number has 6.02 times 10 to the 23rd atoms in it. And that's a mole. So a mole of anything has that number of items in it. So if I have a mole of carbon-12, I have that many atoms of carbon-12. If I have a mole of hydrogen, I have that many atoms of hydrogen. If I have a mole of water, I have that many molecules of water. If I have a mole of golf balls, I have that many golf balls. If I have a mole of moles, that's my pun for the day, then I have that many moles. Don't get them too confused. This is not the same as the little animals. Anyway, so that tells me how many things are in a mole. So if I've got a sample of something and I know how many things are in it, then to find the number of moles in that sample, I just take the number of things that are in it and divide by Avogadro's number. That tells me how many moles there are. But that's often not very useful because, I mean, what's the point of all this? Because we can't count the number of things. We're trying to find a way to avoid counting the number of things by using this concept of moles because it's tough to count 6.02 times 10 to the 23rd things. So typically what we do to find the number of moles in a sample is we use the mass of the sample, which is easy for us to get generally. We can determine the mass of the sample by putting it on a scale and divide by something called the molar mass of the material we are measuring. Okay, that's all fine and good, but how do we know the molar mass? Well, the molar mass is measured. So you can go back in your book to Appendix F, and there you'll find the property of the elements, and one of the things you'll find is a column that gives you the molar mass of every element. Yeah?
Would the molar mass not simply be the atomic mass times
Correct.
Avogadro's number?
The molar mass is the atomic, the molar mass is the atomic mass in grams. Okay? So the atomic mass measured in atomic mass units. So if you go to a periodic table and look at the atomic mass, that number you see there is in atomic mass units.
Right.
If you convert that into grams, then you get the molar mass. If you multiply the mass of a proton or something, if you want it in kilograms, you're going to get a different number. So it's the atomic mass that you see on the periodic table, just converted into grams. And that's what you'll find in Appendix F. So they've already done that conversion for you. So you can just use the molar mass. But that's exactly right, because the atomic mass of carbon is 12 atomic mass units, and its molar mass is 12 grams. If now you don't have an element, you have something like a molecule of water, and you want to find out the molecular mass, the molar mass of a molecule, then you just add up the molar masses of the elements that make up the molecule. So water is made up of 2 hydrogen and an oxygen. If you look back in the table, you'll find out that oxygen has a molar mass more or less 16 grams. Hydrogen has a molar mass of more or less 1 gram. So 2 hydrogens plus 1 oxygen, add that all up, you find the molar mass of water is 18 grams. So you just kind of add things up. The more atoms it has in a molecule, the more molar mass it will have. Then, if you wanted, for example, to know the actual mass in kilograms or grams of the molecule, you could use this. Because the molar mass, the mass of 1 mole, is just the true mass of the molecule in kilograms times, or grams, times Avogadro's number. This is the mass of the molecule in grams. If this is the mass of the sample in grams, so grams cancel out. So now, if this was the molar mass, if the sample was 1 mole, then I'd put 1 over here, I'd put the molar mass here, I'd put Avogadro's number here, and I could solve for the actual mass of the molecule in grams. And find out it's a very small number. So those are the different ways you can move around and navigate around this quantity called mole. That's what it's all about. Then the other thing we did, the other thing we talked about, and we explored in the lab, I got to keep that out of my hand. The other thing we talked about in the lab was that gases, if they are low density, so that they only interact by collisions, they don't chemically combine in any way, so they only interact by collisions, and they're low enough density that the collisions happen reasonably infrequently. They're called ideal gases, and you can actually treat the air in this room as an ideal gas, so it's not a big restriction. Ideal gases, the pressure and volume and temperature are all related by the ideal gas law. And we're going to use 2 forms of it. This is one form. The pressure times the volume is equal to the number of moles of gas. So in this case, we identify volume, or we identify quantity in terms of the number of moles of the gas we have, times the universal gas constant, so that's just a constant, times the temperature in Kelvin. So for the universal gas law, the temperature needs to be in Kelvin. So that's one form. Then the other form of the ideal gas law is the pressure times the volume is equal to the actual number of molecules in the gas. So notice the difference. This is the number of moles, this is the number of molecules. So since the number of moles is the number of molecules divided by Na, essentially what we've done is we've divided R by Na and got a different constant, and that's Boltzmann's constant, which is the thing you experimentally determined in the lab last Friday. So there's the 2 forms of the ideal gas law, and we'll bounce between them as needed, depending on what we're doing later on. So before I moved on to the kinetic theory of gases, I just wanted to do one of the problems from your worksheet, because what we did in lab was we varied the volume and kept the temperature constant, and we varied the temperature and kept the volume constant, and explored 2 different relationships. But there's no reason that you have to keep one of these things constant. The pressure can change, the volume can change, the temperature can change, and in fact even the amount of material can change. The only thing that has to stay constant in the ideal gas law is the constant. So this problem, we're going to keep just the number of moles the same, and we're going to let everything else vary, and it's a pretty basic problem. We may have already done it. I don't know if you guys do your worksheet before class or not, but you may have already done this one. But it goes pretty quick. So I'll let you just think about it for a while. Well, in fact, given the time, we'll just kind of do it together. So we have a sample of monatomic ideal gas, originally at 20 degrees centigrade, 20 degrees Celsius. So what's the final temperature of the gas if both the pressure and the volume are double? So the standard way to do these ideal gas laws is to take everything that changes and put it on the right side of the equation and keep everything that's constant on the left side of the equation. So here's the ideal gas law. That's kind of dim. So we've got PV equals the number of moles times R times T. Well, in this equation, everything changes. The pressure and the volume and the temperature, everything changes but R and N. So we move everything that changes over to the right side, so that gives us PV over T equals Rn. So we have an original pressure and volume and an original temperature, that equals Rn. We have a final pressure, volume, and temperature, and that also equals Rn. These two things are constant, so that means these two things have to be equal. So that leads me to this relationship. And then what can I replace that with? If the pressure and the volume double, then what does this become? 2 pi?
2 pi times 2 vi.
2 vi. So this becomes 2 pi to vi over Tf, or 4 pi vi over Tf. And of course then I've got pi vi on this side, pi vi on that side. So they go away. And multiplying both sides by Tf, then I'm left with Tf over Ti equals 4. So tell me what Tf is. What's Tf? You find
80 degrees Celsius.
No! Why is that wrong? You have to convert to Kelvin.
Oh.
Temperature is in Kelvin. That's a common mistake.
Right.
So watch that on an exam. You don't have to scream and shout like I do. So, yes, the temperature on the ideal gas law has to be in Kelvin, so don't leave it in Celsius. So what's 20 degrees Celsius in Kelvin?
293. No, 293.
293. So T final is equal to 4 times 293, more or less.
Which is
And so what's 4 times 293? Which you'll discover is quite different than 80 degrees Celsius. Okay. Well, actually, you wouldn't be that comfortable at 80 degrees Celsius, but you're going to be a lot less comfortable at this.
this is 1,172.6 degrees, or not degrees, kelvins.
Yeah, well, 1,200 essentially, since we've only got 2 degrees of precision around it, two significant figures. 1,200 Kelvin.
And yeah, it's 900 Celsius.
900 Celsius. So quite a bit bigger than 80 Celsius, right? So remember that temperature has to be in Kelvin. And notice, just by doubling the pressure and the volume, the gas goes up, its temperature goes up quite a bit. Okay, so that's the ideal gas law. Now what I want to do is move on from that and talk about, because pressure and volume and temperature at this level are what's called macroscopic properties of the gas. We just think of them in terms of the gas has so much pressure, the gas has so much volume, the gas has this temperature. But we don't think about what really causes pressure and volume and temperature. But when we look down deeper, when we look smaller, we see that what actually is happening is the reason that a gas creates pressure, The reason that a gas has temperature is because the atoms inside it are bouncing off the walls and moving around. So let's look at why there's pressure, why a gas exerts pressure on the walls of the container at the atomic level. And that'll launch us into the kinetic theory of gases. So, here we're going to confine a gas in a box. And this room isn't quite a box, but it'll do the job. And we're going to look at one molecule of the gas. And that one molecule of gas is just moving around at some velocity v. And so, it's at some point is going to bounce off the wall. And then it's going to move over and bounce off another wall and eventually hit the other wall and come back and bounce off that wall again. And then move around again and come up and bounce off that wall again. And it's just going to keep bouncing off that wall. Well, when it bounces off that wall, it has an original momentum in the x direction. And when it bounces off the wall, what happens to that momentum in the x direction? Changes, right? Because of the force the wall exerts, the impulse, technically, that the wall exerts on the ball. So we know from the impulse momentum theorem that there is a change in momentum of the ball. So suppose we look at just the x momentum for right now, because we're only going to look at this wall, which is vertical, and so the ball is moving, and so the only thing that's going to change is the x momentum of the ball. Because it's moving in this direction, and the only thing that this wall can change is the x momentum of the ball. The x component of the momentum. So the ball's x momentum, since it's moving to the right, its original x momentum is m times the component of its velocity in the x direction. And what will be its final? P final. What does the wall do? What does the wall do to the momentum? Reverses it, right? So it doesn't change the mass, but it changes the direction of the velocity. And what does that do to this velocity again? How do I write that? M dx minus. That's what the wall does. All right, so the change in momentum is P final minus P initial, so that's equal to a minus mvx minus mvx, or it's equal to a minus 2m vx, right? All right, so that's the change in momentum that of the molecule. Now, let's take a look at, remember, that's caused by an impulse, F delta t. Force times time is equal to the change in momentum. That's the impulse momentum theorem. So I can figure out the force that the ball, or the wall exerted on the ball, which is the change in momentum over the change in time. So here's my question. When will this ball next hit the wall? Because the ball can change the momentum when it hits the wall. Then it can do it again the next time the atom hits the wall. Then it can do it again the next time the atom hits the wall. So these time periods, and then, you know, I'm going to have that change in momentum over delta t, and it's going to happen regularly. So if I'm going to get one delta p in that delta t, where that delta t is the time it takes the ball to come back and hit the wall again. So I know what delta p is. What I need to do is figure out what delta t is, the time it takes for the ball to get back. Well, the ball has an x component of velocity, vx. how long does it take for the ball to get back to the wall? Well, we could figure that out since we know its Vx component if we figured out how far the ball has to travel to get back to this wall. Well, how far does the ball have to travel to get back to this wall?
2L.
2L. No matter how it bounces around in the x direction, it's got to hit off this wall and come back. So we know the ball travels 2L, so we can figure out that delta t is distance over velocity. So it's going to be 2L over Vx. So now we know delta t, we know delta p, so I can figure out the force that the ball exerts on the atom is delta p, which is minus 2 mvx over 2L Vx, and that's going to be equal to minus 2 mvx squared over L. That's the force that the wall exerts on the atom. It's not balls bouncing around in there, it's atoms bouncing around. What's the force the atom exerts on the wall?
It's a 2 on
Oh, sorry, I need to, thank you. Then I can cancel those out and get minus mvx squared over L. That's where I wanted to go. Kind of mixed up 2 steps there. So if that's the force that the wall exerts on the ball, what's the force, or the atom, what's the force that that atom exerts on the wall?
Same.
Same, but I got to change the sign.
Okay.
It's equal but opposite by Newton's third law. So the force that of that atom is mvx squared over L. This is on that wall. Okay? Now, the pressure then of that one atom on that wall is force divided by area, right? So that's going to be force, the area of that wall. Now we're doing this just on a cube, so every side is L, so the area is L squared. So I divide this by L squared, and if I divide this by L squared, this just becomes L cubed. So the pressure is mvx squared over the volume. That's from one atom. From the next atom, I'll get Vx squared over V. And this is, I can label them 1, 2, I'll keep just going, 3 squared over V. I'll just keep going, right? For all the atoms in the box. It's going to be huge, right? But mv is all the same. So it's going to be m over v times this big sum of vx's squared. Dot, 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 to vx n squared. Whole bunch of them. All right, now here's the thing. Not every atom in the box is moving at the same speed. There's a distribution of speeds in the box. The atoms are all moving at different speeds. So the way I'm going to solve this, because I don't want to have to make that big sum, is I'm just going to add up all those squared speeds and divide by the total number of atoms in the box, by n.
It's an average.
Right, so that's going to be the average speed. Okay, but then if I divide by n, I got to multiply by n out here. Keep everything square, so I'm doing it by 1. So what I'm going to get here is mn v squared, vx squared average over v. That's the pressure now. This is pressure. Remember, this is pressure. So that's the pressure on this wall. Now, here's the next thing I'm going to say is, okay, I don't like this form particularly, so I'm going to define another term. I'm going to say there's something called the RMS speed of atoms moving in the box. That's the root mean squared speed. It's the average speed of an atom moving in the box. And what's that equal to is the square root of Vx squared. Average. So I square the Vx's, average them all together, and then take the square root. And that's the root mean squared speed in the x direction. Then if I square this, I just get that. So this is the definition of root mean squared speed.
So it's the magnitude of the
So
average.
this becomes mn Vx RMS squared over V. Now I'm almost where I need to get. I've just got to do a couple more things. I don't like having the total number of things in here, but I know what n is equal to from what we talked about before. M is equal to, or n is equal to the number of moles times Avogadro's number. So I can plug that in there. M Vx RMS squared over V. Now then, I'll just switch these around, the m and the n. So I'll get mass times Avogadro's number. Well, what's the mass of a molecule of gas times Avogadro's number?
That's the molecular...
The molar mass. That's the molar mass. So now I've got P is equal to the number of moles times the molar mass, capital N, times Vx RMS squared over the volume. Okay, so one last step then. All I need to say then is if I take a look at V, the velocity of a gas molecule, well, it's made of three components, right? Vx, Vy, Vz. So I say on average, 1/3 of this total velocity is in the x component, 1/3 is in the y component, 1/3 is in the z component. So on average, they're just going to split 1/3, 1/3, 1/3. So that tells me that Vx RMS is essentially 1/3 squared of V RMS squared. The x component is 1/3 of the total velocity. So then I can just get rid of the x here and put a 3 down there. And that leads me to my final conclusion, which is the pressure on any wall now, because I've gotten rid of the x part, the pressure on a wall of the container is the number of moles of gas times the molecular or the molar mass of that gas times the RMS speed of the molecules in that gas times 3 times the volume of the container. That's the general relationship. So now I've related pressure to the speed, the average speed of the molecules in the gas. I've taken a macroscopic property, pressure, and related it to a microscopic property. The speed, the average speed, the RMS speed of the molecules of the gas moving inside that container. So there's the first step in our kinetic theory of gas. I now have pressure related to the average RMS speed of the molecules in the gas. Where this is the definition. Now, let's see how we get this relationship, right? Because we know if it's an ideal gas, we can put in an expression for pressure, right? Because I can multiply. So anybody, can I start erasing some of this now? Everybody. So I can multiply this expression by V. So I get PV now equals, if I multiply this side by V, I get rid of the V on the bottom. So that's just going to give me N times the molar mass times V RMS squared over 3. Okay? But if it's an ideal gas, what does PV equal to? NRT. let's use the RT, because I ultimately want to get an R in there, so we'll use nRT. You could use nKT. Now I've got N, M, VRMS squared over 3. Well, the N's cancel out. Multiply by 3, I get 3RT over M equals VRMS squared. Take the square root of that, and I'm here. So for an ideal gas, the root mean squared velocity is 3RT over M. Well, notice M is a constant, it's a property of the gas. It depends on what kind of molecules are in the gas. R is a constant, 3 obviously a constant. So that tells me the RMS speed, how fast the molecules are going, is proportional to the temperature. The higher the temperature, the faster the molecules are going. That makes sense. And the faster the molecules are going, the greater the temperature of the gas. So now I've connected temperature, a macroscopic property, to the speed at which the molecules are moving in the gas. So temperature and speed are related. Okay, now we can keep going. Continue to have fun. Suppose I wanted the average kinetic energy of one of the molecules. So Ke average. What's that going to equal?
What's it gonna what?
What's Ke average going to be? How would I find that? What's the formula for kinetic energy?
1/2 mv squared.
1/2 mv squared. So if I wanted the average Ke, what V would I use?
VRMS.
The VRMS. So it's going to be 1/2 mv RMS squared. Well, I know what VRMS squared is here, so this is 1/2 m times 3 RT over the molar mass. Big N, big N. Let me write that more clearly. Okay? But what is the mass of the molecule over the molar mass?
Avogadro's number.
Almost. It's actually 1 over Avogadro's number.
No, the inverse.
Yeah. Because remember, if I have
M over N times Avogadro's number. So
if this is the mass of one molecule, then this is the molar mass, and this is going to tell me the number of molecules in a mole, which is equal to Avogadro's number. And I've got the inverse of that. So I get 1/2 times 3 times RT over Avogadro's number. But what is R over Avogadro's number? R over Avogadro's number. What is that equal to?
Okay.
Boltzmann's constant. So that tells me that the average kinetic energy in a gas is 3/2 of Boltzmann's constant times G. So now I've connected the average kinetic energy of all those molecules flying around in with the temperature. Okay, that's cool. What would I do if I wanted the total energy
added some work.
in a gas? No, I just want to know the total energy of a gas. I'm not doing any work now. I just want to know the total energy of the gas. This is the average energy of one molecule of the gas.
Oh, I see.
So what would I do to get the total energy in all the molecules in the gas?
Multiplied by the
So you need
molecule.
just total kinetic energy.
Total kinetic energy.
Just multiply by the number of molecules.
Multiplied by the number of molecules. Okay, so I need the number of molecules, so the total energy is equal to the number of molecules in the gas, but the number of molecules in the gas, what's that equal to? N. The number of molecules in the gas is equal to Avogadro's number times what?
Small n.
Number of moles. So, if I take E equals the number of molecules times the average KE, average, that's going to be equal to N times NA times 3/2 KT. But NA times K, that gets me back to R again, right? So this becomes 3/2 of the number of moles times R times T. So for a monatomic gas, the internal energy, all the energy in that container, is 3/2 times the number of moles in the container times R times the temperature. I increase the temperature, I increase the energy. Decrease the temperature, decrease the energy. Now this is for a monoatomic gas. Why am I stressing that? Because this is based only on the average kinetic energy. And that average kinetic energy was based on the average translational speed. But what other kinds of kinetic energy can I have? Where else can I get kinetic energy besides moving along a straight line?
Oscillation.
Oscillation? What else?
Vibration.
Rotating. Rotating. I can get it from rotating. So, if I'm just a monatomic, if I'm just a single atom, like helium or neon or any one of those gases that don't combine with anything else, those are monatomic gases. Right? Oxygen is a diatomic gas. To make oxygen gas, you take two oxygen molecules and put them together. So, that, in addition to moving, can also rotate around an axis. So it turns out you can actually get more energy there. I'm going to go back to this. Did I skip that? All right. Oh. Now I got ahead of myself. And we'll come back to this in a later, but it turns out that each one of those modes, I'll come back to this later, each one of those can give you an extra degree of freedom. So you can have energy in the rotation and energy in the vibration. We'll come back to that in a second, though. I forgot, I got ahead of myself. So I'll come back to that in just a minute. Before we're there, let me go back to this. All right, so we got all of them. So this is just the energy in translation.